Okay, hi. Sweet. Y'all guys can hear me. So let's get down to the business. Exam review 2 for data structures. So this exam is very extensive, especially with the sorting algorithms part of it. Sorting is a very long topic as y'all guys could tell, but we also have to cover queues, stacks, and also hashing, which is something new you guys learned. So let's get straight down to the business because sorting is gonna take a little bit longer, but that's okay. That's why we're here. So the first sort you learned, hopefully in 1437, or if you read the textbook, it should be in the textbook as well, is bubble sort, aka considered one of the worst sorting algorithms to ever exist to man. And why is that so bad? Well, because you're comparing every single element that's adjacent to you from left to right. And if they're out of order by any chance, you have to swap every single time. No exceptions at all. And if that takes a while, especially for like let's say an array size of a 1000, it's gonna take like ages to compile. So we don't recommend bubble sort, but it's very good to know and good to learn from our mistakes, especially from in the past. So a few takeaways here is to know your time complexities. Know that bubble sort always has a worst and average worst time complexity of n squared, no exceptions. But why is that? Which is going to be your to-do list. So you can learn, so you can study and get engaged along the way. But I'll give you time to answer that, but probably after I explain how bubble sort works. But let's move on for now. And then the best case scenario is O of n, and that one's pretty easy. Only reason why this is O of n is because the array is already sorted. We only have to do one pass through the whole entire array from the start to the end. That's O of n. Pretty simple. But why is it n to the power of 2? Like n squared, n squared. That's how you say it. That's because you have to swap. So let's say, for example, our first pass is comparing 7 and 6. And currently 7 has an adjacent element of 6. And hey, 7 is bigger than 6. We have to swap. So we swap again. Now we compare 7 and 4. It's the same thing again. Swap again. 7 and 3, we swap. That's why we have 7 down here as well. In the second pass, we're comparing 6 this time, where 6 is bigger than 4, so we swap. Bigger than 3, so we swap. And then now we finally leave it position right there because 6 is not bigger than 7, so we do not swap. And in the third pass, we finally do one last pass, comparing 4 and 3. Since 4 is less than 3, it's a little bit out of order, so we need to swap again. So now we swap 4 and 3, and then we're done. Sweet. Now, this is an issue because you're comparing every single element, if it's bigger or not, or if it's smaller, depending on the number you have as well, to be honest. So that could be a really bad issue, especially time complexity wise. The reason why is because it's n squared is because worst case scenario, the whole entire thing is unsorted, like this example right here. And if you notice, we did multiple swaps, more than the actual array itself. You might say n squared times, or we could just say we've done this pass multiple times. So since we have to compare, even if we don't swap, we have to compare every single time, which is why it's gonna be n squared, because that's a huge issue. And the explanation for time complexity is that the worst case scenario, you have to compare every single element inside the array n squared, and you have to swap every single element as well n squared. So the time complexity is to be O of n squared, which is a horrible thing. And in case you need help visualizing it, I have provided links for every single slide that are workable because I own these GitHubs. So I hopefully they stay public and don't get taken down. So if you ever are curious, you can take a look at the code right here. And if you need help visualizing how bubble sort works, I provided links to this amazing website that I use when I was taking data structures. And this website has multiple sorting algorithms you can run. So it's not just bubble sort exclusive to that. So you may see that link multiple times because it's good to have everything in one place. So yeah, there's code for every single sorting algorithm, including the ones we're never going to touch, like bubble sort, but it's good to know. And it's also good to know how to use them. And yes, they're very extensive in detail. You can check them out later, but just a little note for y'all since the Replit thing isn't working right now. So little alternative. So let's move on to insertion, which is something you learned this semester. Insertion is shockingly bad as well. Same time complexity as bubble sort. And the only reason why we learn insertion is because it's the start of sorting algorithms, like better ones, even though they're the exact same thing. And this one takes a book out of bubble sort where we have to iterate instead of doing it recursively. And we have to insert at each element of an unsorted array into the correct position, which can take a while, especially if if it's in a whole entire unsorted array from like, let's say descending order, and you're trying to do ascending order, you have to insert multiple numbers at every single pass. So for example, let's look at this little sketch right here from Geeks for Geeks. So here we're trying to compare 23. And 23 is bigger than 1, so we keep going to the next pass. 23 is bigger than 10, keep going. However, we're doing some inserting. Remember, it's insert. So we're comparing 23 and 1 first. This is our element we have chosen, and this is the one we're trying to compare. And since 1 is smaller than 23, we can assume that, hey, 1 will go to the first position. So we just set that as our current goal. And we swap again. Hey, I've seen, now I'm trying to compare 23 and 10, but keep in mind, we have seen 1 already. So we can assume like, hey, we could just insert 10 between 1 and 23 because for 1, 10 is greater than 1, but it's less than 23. So that's the perfect position for that number. And then we insert 10 in between 1 and 23, nothing else. And then we compare the next number, which we can use 23, but we have to use every single number now at this point. 5, let's use 5 now. So 5 is less than 23, less than 10, but it is greater than 1. So we place 5 in between 1 and 10. We insert that node right there. And then finally, we compare the last number, 2, and 2 is less than 23, less than 10, less than 5, but greater than 1. So we place 2 in between 1 and 5. And there we have our sorted array. And you can visualize that here, same link, and you can also see the code as well on how that works. And so time flex exact same thing. Best case, it's already sorted. You just do one loop, making sure you compare the whole entire thing itself. Worst case is either descending or ascending order. Basically, you're going from descending and you want to sort it ascending order, or it's already ascending, but you want it sort of descending. That's a horrible thing because you have to insert at every single element. You have to insert each element into the array, which is the worst time close. You have to do every single variable at least once. And like bubble sort, it's n squared, which is horrible. Now let's move on to the selection sort. Also, if you can't tell yet, I'm just covering the algorithm, not the code. That's because code is important. You have access to your code through Zybooks whenever there's coding algorithms, but code-wise is really important for practical uses. And this is your exam, more theoretical, especially for the theory portion. And for your programming section, you have Zybooks. You can just look back at your old labs and use that as your programming. So going more towards the idea of how sorting works and less practical wise. But you can also look at the code anytime you want. All these have code. They're all made for those specific sorting algorithms, which is good. So if you're not used to this type of format, that's completely okay. It might take a while to get used to, but trust me, it'll be worth it at the end. Now, the next one is selection sort. So selection sort is also another iterative type of sorting algorithm, which is not the best time complexity. You might tell it's also one of the worst as well, but it's very good to understand how this works. So, reading this short paragraph, the algorithm will basically repeatedly select the smallest or largest, depending on how you want to sort this, from a unsorted party array. So just one small portion, like a subarray, you might say. And you want to swap it with the first unsorted element, gradually growing the sorted portion into the entire array sorted. Nothing else. So the reason why we're learning this and to reviewing this is because we need to know how subarrays works and how we can use that to make more efficient algorithms in the future. So for this case, we're trying to find the smallest number, and we're gonna swap only with the first value. So let's do that real quick. So for this case, 2 is my smallest value itself, and we're going to swap it with the first position, which is 7. So we swap those two elements right here, and now we can see that 2 is already in the sorted array, and then these then 5, 4, 7 are not sorted yet. So we're going to keep them separately for now. And then we do it again. We find this next smallest one, which is going to be 4, and then we swap with the first position, 5. And so now we do it again. We have 2 and 4 in the correct position from smallest. So we know 2 was the smallest, then 4 is the smallest, but 5 and 7 are still in the unsorted array. And then we check again. 5 is our next smallest number, but it's the first value. So we don't swap, but we still move that to the sorted array variable. And then now we have one more unsorted variable. And since that's the last variable itself, we can assume that this is the smallest. And since it's the only one, there's no need to swap. We just have to add it to the sorted array. And that's it. That's how selection work. So depending on how you want to order this, either through ascending or descending, for ascending, use the smallest one. If you're doing descending, choose the largest one, because you want to check every single value, find the smallest one, then swap with the first position. Nothing else. And then the reason why it adds time complexity of n squared is because you have to iterate through the whole entire array, and you have to find the smallest one, which is horrible time complexity, because you have to go through this array multiple times. N times, if you're way more precise. And since we have to add it to this sorted array, which is all one, not too bad, but we keep breaking it down, but the size never changes. So that's, again, O of n as well. So we do 2 loops, one for the find the smallest one, and another one to actually get to iterate through the whole entire array itself. It's n squared, which is pretty bad time complexity. But for this class, it's not too bad. Excuse me. So now we want to merge sort, one of the more faster ones, you might say, even though time complexity is still pretty bad. But compared to selection and insertion, practical, it's pretty fast. So unless I forgot to change it, but let me double check, because I'm pretty sure I forgot to change it. I need to. Pretty sure it's nlogin. Yeah, it is. Of course I did. So sorry for this minor inconvenience, but yeah, basically that's wrong. So for merge sort, one of the best algorithms and one of my favorites, time complexity wise will always be the same thing, which is going to be O of n log n. Completely my mistake on checking that part, but yes, merge sort is one of the more fastest one. It's because it uses divide and conquer principles, where you have to recursively divide the actual array itself into smaller subarrays, and then sorting those smaller subarrays and then merging them back together recursively wise. And to explain this real quick, let's choose a array. So the array size has roughly, let's say, size of 7. So let's divide this into 2 parts, either 4 and 3. But we're not worried about what value to sort yet. Not just yet. We're just trying to break this down into smaller subarrays. And since 4, we can divide into 2 and 2. And as 3 value, we can do 2 and 1. Keep halving our arrays every single time, and until we half it until we reach the one level. Once we reach the 1 level, now we can start sorting. And from here, we can start comparing which is smaller, which one's bigger. And from here, we can see 27 is smaller than 38. So we put 27 first, then we put 38 between 43 and 3. 43 is bigger than 3, so 3 goes first, then 43. 9 and 82. 9 is less than 82. So we put 9 first, then 82, and then 10 just by itself. And then we recursively sort it again. However, we check both values this time. We will check 26, 38, 3, and 43. So between those 3 values, which was the smallest one? Well, it's going to be 3. And then from there, 27, 38, 43. We just recursively merge them back together. And then same thing here. We compare all values this time. 9, 82, and 10. And then from here, which one's the smallest one? 9. So we put 9 first. Then 10 is the smallest, next smallest one. And then 82 is the biggest one. And then again, apply the same principles here. Look at this whole entire array itself with this array and it merge them both together until we get our finally sorted array, which is very nice for time complexity wise because you keep halving your array every single time. And then when we're merging back together, that takes O of n because we have to merge it back to the original size, which is the input size itself. So it's much faster than selection, insertion, and bubble sort, way faster than that. And the only reason why it's faster because we keep halving our into smaller subarrays until we reach that one. That's why it's a lot faster because we're breaking our workload into halves. And that's what's one of the more important algorithms to know. And so yeah, sorry for the mistake. I'll fix it in the actual release. But yeah, that should be n log n. Hopefully I didn't make the same mistake. Oh, I didn't, thank God. So quick sort. Another divide and conquer principle here. However, instead of halving our array every single time, let's choose a pivot this time. And we're going to partition the array according to the pivot itself, aka divide the array into smaller, the left-hand side, and into bigger values based on the pivot itself. And it will recursively do it again and again and again until, for the left and right partition. And this one, same time complexity as merge sort, because best case scenario, it's already sorted. But you still have to choose a partition spot itself. But it's not too bad because you keep halving it, but you don't have to do multiple like swaps and then keep dividing to like and then merging it back to one single partition. Don't have to worry about that at all. But if it's unsorted, and the worst case scenario, which is either ascending or descending, depending on how you want to sort your algorithm, you get n squared, which is why it's kind of sucky. Even though practically wise, fun fact, quick sort is faster than merge sort practical, like in real life. So weird, but it is, no matter what. Even if the time complexity is worse, theoretically, this one sucks. In the real world, it's pretty good. So as we said before, we have to choose a pivot. So let's say based on the lab itself and based on what you guys learned in dance class, we always choose the right-hand side, which should be 13. Oops. 13 is our pivot. And then from here, we choose the values based on our pivot. So left-hand side, which is right here, should be less than the pivot itself, which is why I left. And then we have right-hand side. So if you look down here, it can be less than or equal to 13, or it can be greater than or equal to 13, depending on how you want to do this, but theoretically it should work no matter what. So if you focus on the values in here, you can all tell that the values are less than 13, like 7 is less than 13, 12, 4, and 11, nothing else. And if we check on the right-hand side, we can see 18, 15, 79, and 6. Oh, I think that's 19 is bigger than yeah, it's 19 is bigger than 13 itself. And then we recursively call partition again. Remember, we take the right-hand side. So again, you do the left-hand side, get the left-hand side partition, which is the most right index itself, partition that value until you reach the one index variable like 12, and then basically you're done. And you do pivot again for 4 until you reach the last one itself. And then you do the right-hand side as well. Once you finish the left-hand side, you do the right-hand side, where you do 16, right-hand side, 16 is new pivot, and then we have 15, which is basically means we're done. We have two variables right here, so we chose the right-hand side again. So we choose 18, and then we split this into left and right-hand side, where it could be less than 18 or equal to it, or it could be greater than or equal to 18. And for our case, it would be 18 for left-hand side, and 19 for the right-hand side, because 19 is bigger than 18. And then from here, we have already basically sorted our whole entire algorithm just by dividing it into halves. And we just put it back together whenever we recursively call this algorithm again. And so, using that exact same principle, another fun fact is that you can use the exact same divide and conquer, same pivot, and same partition principles for quick selects. But I'll let you guys go into research on how the time complexity wise is a little bit different than should be O of n, best case scenario. But And just to let you know, quick select is just finding the smallest or largest kth element in an unordered array. But as a little homework for y'all to study, tell me why the partition is the time complexity is so different, even though they use the exact same principles. Ask me for your homework for tonight. So let's go into heap sort because I want to get this sorting in less than 30 minutes because we have to get over sorting, even though it's my favorite topic. So heap sort, you can either do it by max heap or min heap. But let's cover the first scenario, which is max heap. So in a max heap, the algorithm will find the largest max element, we'll swap it with the last one, and repeat. Which sounds a little bit awfully strange, like similar to you might, I don't know, a selection sort. It's kind of crazy. And if we use a minimum heap, we use exact same principles, except we just use find a minimum element, and then we swap with the first value, like selection. Strange, but template is a little bit different. Why is that? That's because remember we're bringing it down to smaller subarrays every single time, which is good to know because we build a heap and heap takes at least log n because heaps are like extremely fast. And if you don't know how heaps look like, they're just little binary trees and they're so cute, little and they're so small. But that's why they're so fast because you use a tree to make your sorting a lot faster. And for this case, it's our max heap where you find a maximum element, which in this case is 91. And then we build a heap based on 91. So 91, and then on the left-hand side should be less than 91, which is 40, which is true. And then we have 22 as well. Oh yeah, because we're inserting into the root itself. So you have 40, 22, and then you have 1, 9, and negative 15. Just to get used to a max heap, because we make sure we want to find the largest value every single time. And then from there, we break it down to smaller value. So let's say, and then from there, we can swap with the root with the last element and heapify the root again. So basically, swap 1 and 91 every single time until we get that maximum value itself. And then heapify until we heapify the root again to get that final array. Or in other words, looks like this. Basically, find the maximum value. So our maximum value is 91, right here. And then we're going to swap with the root itself. So with 1, that's why 91 is now on the root hand side. And since 91 is the biggest one, we can finally say, hey, 91 is the biggest one. Let's put this into the back of the array. And then let's do the next level. So now we find the next biggest one, which is 40. Well, right here, we swap with the root, which is 1 again. And so we do 40. And then we swap that. And then because you don't have to worry about the details, just worry about swapping this first element and the last element. And then from there, you'd be like, okay, sweet, let's put 40 into that array. And then keep going until you reach that sorted array. A little bit visually wise, a little bit more different from what Dan taught, but exact same principles here. You keep repeating until you reach that last element. And so you can visualize it down here as well. And which is a little bit different website. Well, same website, different link though. And then the code is also here for both minimum and maximum heap. They're just under different folders, so you just have to dig a little more deeper than the other usual code, but they're in there, I promise. And so now let's not worry about like actual code. Let's worry about, I don't know, actual mock questions. Shocker. So this mock question entails in using quick sort to sort on this array. You have to sort in ascending order. So it's pretty easy. We just have to choose our pivot point. So our pivot point, based on what we learned, is always on the right-hand side value. So let's choose 3. And so let's call this array real quick. But let's already partition this array to have 3 in the middle value, and anything on the left-hand side should be less than 3. Anything on the right-hand side should be bigger than 3. So let's divide this up real quick. So we will have 3 in the middle. So we have pivot 3. Oh, make it a little bit bigger. Yay, 3. And then we have based on the order. Let's read it real quick. So our next value, so let me do this real quick. Here's our pivot, and let's use yellow for now. So what's our next value? So next value is 4. And since 3 is our pivot, let's break it down real quick. So we have 4, which goes on the left-hand side. 4, and then we have 1, which goes on the right-hand side. I mean left-hand side, and we have 2, which goes on the left-hand side. And then we have 9, which is bigger than 3. But since 3 is our pivot point, we also need to swap 4 and 3 to make sure we have the correct partition. So let's remove 4 for now, as we need to swap this first, because I completely forgot the steps already. So let's do this real quick. So we do 3 as our partition spot, and then we keep the array as is. So 1, 2, 9, 5, 8, 4. There we go. Makes a lot more sense now. So let's divide this real quick. So 1, 2, those are pretty good still. Yeah, 1, 2. Then we have 9 next as our next value, but it's bigger than 3. So we put this 9 over here. And then we have 5 over here, where we divide this up again, right there. Then we have 8, which is bigger than 3. And then we have 4, which is also bigger than 3. Sweet. Now we have the first level of this array itself. So now we have split it to separate arrays. Sweet. We also swap the first element with the last element just to make sure we have our correct pivot value itself. And something you did in your algorithm as well, which I need to actually show. I mean, I'm not used to it tracing wise, but now sweet. Now we can look at the next level, 2 and 1. So we can see 2 is our next biggest variable. But quick question, it's sorted already, right? So we don't really need to break this down any further, because if you do break this down, you're just gonna get this. You swap, so you just get 2 as your pivot point, and then you get 1. And then again, 1 is your pivot point, which just means you're done. So to simplicity wise, we can just say this. We can just say 1 and 2 is sorted. You're done. But the other array is not sorted at all. So same rules apply here. Choose the right-hand side of your pivot, which is going to be 4. And so now let's swap real quick with 4 being our pivot. So 4, oops. And then we swap 5, 8, 9. Sweet. So we have 4 as our pivot. It's make a box to show the pivot itself. But quick question, well, the problem is this pivot going to have a little issue. Our left-hand side is going to be empty because none of the values on is greater than 4 or less than 4. They're all bigger than 4. So we have 5, which is bigger than 4, 8, and then 9. And again, we split it again, but weird part is this is already sorted as well, because we have 9 as our pivot, so we can do our alternate steps again, but we're never going to swap. We're not going to exactly swap, but we're going to never be satisfied because it's already sorted. And if it's already sorted, you're done. So at each step, we can just draw it out on the side. We can say that our array keeps our array has a sorted step at each step as to follow. A little bit weird sentence. I should really fix that later, but doesn't matter. So we have our pivot, which is going to be down here. 1, 2, 3, 9, 5, 8, 4. Cool. And then we do it again for the next one. We can say down here we have 1, 2, 3, 4, 5, 8, 9. Like that. basically done. So you have sorted this algorithm using quicksort. A little bit janky ass tree, not gonna lie, completely my fault, but it's good practice to know that you can make mistakes. And once you know you're done sorting, you don't have to sort. You don't have to do any pivots anymore. You're basically done. So this is completely valid. This will work if you get this question in the exam, but that's a big if. So let's move on to the next question real quick because we have like multiple questions. But yeah, here it is right here. Except I skipped like the swapping part of it itself. But if you want to be more specific, you can look back to this one up here. So yeah, let's move on to the next one. Mock exam question 2. However, this time instead of using quick sort, we use heap sort. And we still use ascending order. However, since we're using ascending order, we're going to use a max heap to satisfy this array. So to break this down a little bit more, we're gonna use max heap. So find the biggest element, swap it with the first position, and heapify again and again and again until you satisfy the whole entire array. So let's break it down real quick. So in more detail compared to the horrible drawing I did earlier, we have to heapify by 9. So let's do a max heapify. So we have 4, 1, 2, 9, 5, 8, 3. So let's heapify. So let's call this H. H for heapify. And for this case, we're looking at the biggest number since we're looking for the maximum, which is 9. And since 9 is the biggest, we need to make sure we swap correctly and keep swapping until we make 9 reach the root. So let's swap real quick. And then so we swap 9 to the root. And while we swap 9, we keep swapping some other variables as well as we're trying to find our maximum heap. So we swap 9. Then we swap 5 as our next biggest value. Then we swap 8 as our next biggest value. And then once we reach the next value, which should be swapping 1 into the middle position, we swap 4, 2, and then we swap back to 3. And it's a very strange swap, right? Because we're not swapping just the first position. We keep swapping the whole entire array. Basically, since we're using max heap, each parent is greater than its own child. That's the rule. So how does it look like? Because it's very interesting how we have to swap, since we have to make sure each child satisfies the root. So let's show it in practice. So we have 9 as our root. And then from here, we have 5 as the left child. And you have 8 as the left child, which satisfies the rule, right? Uh, the parent is greater than its own children, which is true. 9 is greater than 5 and 8. So we go to the next one, 1 and 4. And then we can say 1 has a parent of 5, which is 1 and 4, which 1 and 4 is less than its parent, or a parent is greater than its own child, which is true. 5 is greater than 4 and 1. And then we do the next heap, we have 2, 3, which is also true. 8 is greater than 2 and 3. So when we swap, we try and make sure this looks just right as we do, as it looks like as a max heap tree, we do into the array instead. So let's keep going. So now we're trying to find the next heapify. And while we do the heapify, we know 9 is our biggest value already. So we can store that at the very end. So let's write this array real quick. Let's heapify this one more time. So when we heapify, we have to swap the last variable, 3, and swap 9 again. Because now we know 9 is the biggest one ever to exist. And we can move that back to a sorted array or move it to the back. And now mark our sorted array as green. So we have swap 9 and 3. So 3 will go to the beginning now. Then we have 5, 8, 1, 4, 2, and we have 9 right here in our sorted array. So now let's heapify one more time. And our next biggest value is going to be 8. So following the exact same principles again, let's draw this out. So we know that we will not include 9 in this next heapify. So we have 8 as our root. So 8 needs to go first. And we have the next two values, which is 3 and 5 in this array. We know 3 will be less than 8, but it doesn't really matter. But in my principles, this works like this as well. But we know 8 is greater than 3 and 5. Sweet, that is true. But now we have to make sure the rest of the values are correct. So we need to know 1 and 4 and 2. So 1 and how do I say this? 3 is greater than 1, but 4 is not greater than 3. So this will not work. So let's go back to the beginning and see what other value we can use to show that this heap file tree will work. So let's swap 5 and 3 instead. So swap 5 and 3. So swap 5 and 3. So we have it like this. Now let's keep going. So 1 is less than 5, which is true. And then yes, 4 is less than 1. Sweet. So we can add this to our current array. And let's check 2 real quick. 2 is also less than 3. Coolio. We have our next swap done. And then make sure we include 9 because we need to make sure this array doesn't lose track of its other numbers. Now we swapped. Sweet. Now you apply the exact same principle again. What's the next step? Heapify. But since we need to heapify, we just swap our other values this time, which is going to be 8 to the back of to the last variable and the unsorted array, which is 2, and store where 9 is at right now. So let's heapify this real quick. Well, we heapify, let's find the next smallest, biggest number. So we have swap 8 and 2. So 2 will go to the beginning. We have 5, 3, 1, 4, 8, 9. Next step is heap. So from here, we need to find the biggest one again, and that's in our next parent or root node is going to be 5, because 5 is the next biggest value. So let's draw it out again. So 5 is our parent, and then we have two values, 2 and 3. But if we can see into the future, but that 4 will never satisfy our condition. So we need to swap 4 into the next value. But let's see what happens first. So they have 2, 3, nothing wrong with that. Let's see, 1 is less than 2, sweet. But 4 will never be less than 2. That will never be true. So we need to swap 4 and 2 to make sure 4 will go first. Then we'll check for 2. Or in other words, rearrange our heap. So we have, this is our original one. So let's change it real quick. So our next biggest number will be 4. Since this is max heap, we need to keep looking for the next biggest number. And then again, we will have 3 because 3 and 4 are less than 5. But 3 or 4 are like the next biggest value in our heap. And then we check again, 1 and 2. And we can place that on the right-hand side. We have 1 less than 3. We have 2 less than 3 as well. And then look, our heap has satisfied. Since our original one did not work, this satisfies our new heap. So let's write this down real quick. So we have 5 as our parent. We swapped 4 and 2, which is here and here. So 4 needs to go first. So this heapifies it all over the place right now. Move this down here, move it over here, put that right there, there. Used to look like this a little more, way better. And since we're going in order, like that. So once we swap 2 and 4, since 2 will never satisfy 4, then we have 3 as our next one. And then we have 1, 2, and our original sorted array, 8, 9. Just to make it more generalized, like the algorithm itself. And you keep going again. Since 5 is our parent and it does satisfy our maximum heap, we can say we are done with this step, and let's move on to the next heapify, since this was our swapping phase. So remember, make sure whenever we heapify, 5 will now go to the back of the array or this sorted portion of it, and then 2 will go back to the front. So we're going to first swap 2 and 5. So we have 2 in the beginning, 2, and we have 4, 3, 1, and we have 5 into the sorted portion, 8, 9. This is our heapifying step. So looking at this, what's our biggest number? That's going to be 4. And so we have to make 4 as our root. And so once we make 4 as our root, we actually don't have to swap, unironically, since if we draw this heapify real quick, yeah, 4 as the root, and we have 2 and 3. So we have 2 right here and 3 on the right hand side. And let's check. Does it satisfy? It does. 2 and 3 are less than 4. Sweet, we're good. Now we have one more variable, which is 1, and we can put that one over here, where 1 is less than 2. Yay. Remember, we keep adding the elements based on their order in the array, and we always move it to the left-hand side first, every single time. So now we know 4 is our root, and we have 2, 3, 1, and then our sorted portion, 5, 8, 9. And then it's our swapping phase. Remember, now we have our maximum value, 4, and we just swap it with 1 now. So our next step, heapifying, is 1, 2, 3, 4. Oh, where 4 is in our sorted portion now. 4, 5, 8, 9. And then our next step, heapify a couple more times now. We're almost at the end, a little bit long-winded, to be honest, but it's good to know how to do each step individually, even though it's a little bit more tedious now. So what's your biggest value? 3 again. And so let's double check. 3 is our root now. So 3 is our root. So 3 needs to go first. And then do we need to rearrange? And the thing is, we could, and technically we kind of have to, but it's not a requirement right now. Since we can say 1 and 2. And on the answer key, we do swap those variables, but at the end of the day, it will not make too much of a difference. But if you want to, you can swap these variables, saying that our 2 needs to be our first value inside this array. So we find 2 as our next biggest value. But for now, let's swap it for now for the sake of simplicity. So we say 2, 1. So, oh yeah, swap these variables. We have 2 on the left-hand side and then 1 on the left-hand side, right-hand side. And then we have our sorted portion again. So we have 4, 5, 8, 9. During our swapping phase, we swap 2 and 1 to make our life a little bit easier. And then we have 3 as our parent root, which is our largest child for the time being. And yes, once we do that, we need to make sure we move 3 to the sorted portion of the array and then heapify once more. We're almost done, I swear. We've gone from like seven values to 3 now. We're like basically almost there. So let's make sure we heapify this array now. So we need to swap 1 and 3. So we have 1 at the beginning, then 2, and then our sorted portion has 3, 4, 5, 8, 9. And now it's our heapifying step, and then make sure we find the next biggest value, which is 2. And then from here, we make sure 2 is our root. So let's say 2, and it is only at one value. We give you 1. And there we go. And since we have to swap 2 and 1 to make sure 2 is their parent node, we can do 2, 1, then we have our values 3, 4, 5, 8, 9. This was during our swapping phase, where we swap 2 and 1. And then from here, we finally get to put 2 into the sorted portion of the array. We have 1 left, and we have 2, 3, 4, 5, 8, 9. And we have heapify one more time for 1. Or you can just say you're done. But for our case, we can just say heapify 1, where 1 is our last node. And since this is our last node, it does satisfy the max heap conditions, as we can say no child exists. So we're done. And since no child exists, you're done. You can just say 1, 2, 3, 4, 5, 8, 9 is your sorted array using heap sort. Yes, a little bit more different compared to like merge sort, quick sort, but just draw a binary tree and you'll be okay. But yes, and make sure whenever you're swapping, make sure the first node is always the parent node when you're swapping. And then from there, the adjacent nodes will be the child, will be left hand side to right hand side, left and right, left and right. But just little good tips to know. So yeah, and in here is our correct answer key. And so yeah, we're good to go. I know that was a little bit more heavy, especially for a good almost an hour on one topic, but it's also a good time to make sure we have a brain workout time and little fun facts and a little bit more torture vibes. You can use sorting algorithms for any data structures, anything in particular. Since the code covers mostly dynamic and static arrays, but mostly static arrays, you can use sorting on array list, dynamic arrays, vectors, linked list, which is very fun to do. You can also sort stacks, queues, and automatically hash tables. But if you want me to recommend something, I would recommend sticking with dynamic arrays, stacks, unironically. That one was just for fun, but definitely focus on dynamic arrays and linked list. But it was good. It would be good to know all of these. But definitely those two I mentioned to study and know how to implement as well. So you can have like a good idea how those sorting algorithms work statically, but make sure how they work with different data structures. And another hint for the exam, you should consider what other algorithms are considered sorting or searching. Like, for example, binary search is not considered sorting, even though you technically do use the same principle as, let's say, quick selects, where you're trying to find a value, but for quick select, you'll only find the smallest value, not just any value. So it's not considered sorting, but it will be good to know what are their time complexities. And so yeah, as a little bit more hints to what's gonna be on the exam, but just also stuff to know for fun. Like whenever someone asks you, like, hey, what is this complexity for? Hey, can you do this shit? Can you do this for a linked list? Like a merged linked list is very fun, very hard to do it the first time, but pretty sure it's one of the most common Microsoft questions, interview questions ever, which is one I love. But sadly, I didn't get that, but that's okay. So just something to get used to. So yeah, hopefully after that small little break, hopefully we'll be ready to continue our adventure ahead. Okay, queues. Queues are very important, especially since the queues follow first in, first out principle. Just saying, the first one in the queue is the first one to get out, nothing else. And you can visualize it here using a different link this time. And you also have the code of it as well, which covers a dynamic array. Something I think it's a little bit different from your labs, but it still has this general idea, especially for NQ and DQ, and how to implement those as well, which is good to know. Hint, hint. So NQ just pushes an element to the back of the queue. It does an O of 1 because you always know you always have access to the back of the queue, especially if you declare a back variable. And since queues are very optimized, especially when you get to priority queues, you can just push an element in O of 1 time. And to DQ is the exact thing as removing head from a linked list. You can just do it in O of 1 because you know what the head is. And it's pretty easy. You just do, hey, you're the head, get out of here. O of 1, pretty fast. So knowing that general structure where queues are first in, first out, we can go something a little bit more advanced and use priority queues, where we will DQ based on the highest priority. And we will also simply use the exact same NQ principle as we're going to push an element to the back of the queue in that order, in an order. So let's say I'm pushing 1 with a pretty low priority, but let's say I'm pushing 20, then when you DQ, you have to look for the highest priority and DQ that from the queue itself. So it's basically like a very fancy delete, but we're looking for the biggest number, nothing else. So NQ O of 1 again, because you just push them to the back, but DQ of O of n because you have to look for the highest priority. And then once you look for it, you kick it out in O of 1 time, but you have to look for it in O of n time. Good to know. Which I have also coded in priority queue, which is good to know, especially if you're for these next mock questions. And you can visualize a priority queue as well using a visual.go.net visualization. So speaking of the devil, let's talk about a priority queue using linked list only, but let's only implement the enqueue function itself. So in the answer key, I provided the whole entire thing itself so you can see how it works. But in the actual exam, you're not going to be asked to do that. You're probably going to be asked to do it either in Zybooks and theory portion, or a little bit of both. Who knows? So let's get a little bit more dirty with our hands now this time. So a priority queue will be used via linked list. So a little refresher on linked list. Linked list has a few properties, including that they're pointers and that you have nodes, where each node in this queue will have the value itself or the data, the priority, and the next pointer itself. A VPN, scary, but that's okay. So it'll basically look something like this, where the next pointer will point to the next node itself, but we will only DQ based on the priority. So it's really important to know what is your priority. And so for this case, we're going to insert based on the priority order itself. So let's say we want to insert this, look at this, where we have to redeclare our p values. It's scary. We have to redeclare our VPN values. Shift my tempers, I guess. So real quick, so we have values 1, 2, 3, but these have a priority value of 0, let's say 5, and this will be 20. So 3 will be the next value to DQ. But I want to add a value, which is what we're trying to focus on in Q. So I want to in Q, let's say the value 4 with a priority of 1, and our next pointer is still currently null. So to insert this based on a enqueue with a certain order, we need to enqueue based on P. So we can see it is bigger than 0, but it's less than 5. So we have to reorder our linked list to where 1 will point to 4 this time, and then 4 will point to 2. So we have a priority status of 0, 1, 5, 20, which is correct, which is the order you want to keep it in. So knowing that little theory, let's create a enqueue function that will take care of the order. It will incorrectly insert into the array, and it will keep track of the actual priority values themselves. So I should really add a new page here, but oh well. We'll make use of what we have. Let's do this in pseudocode, just for so I can save room. But the answer key will have it in C++ code. So it's just something a little bit more easier to read it whenever you're done in the future. So have your function, call it enqueue. So you're gonna do n, I misspelled that one for sure. Enqueue function. And we have two variables. We have data, which is the data value itself, and we have the priority based on the priority value itself. And so we to make a new node itself, so we can make a node pointer that will be a new node, which is node we want to add. So for a new node was basically in our tracing, but this was our new node. And we need to make that via a class that you don't have to worry about. So we can say new node, give it data, D for data. Yeah, I'm running out of space. D for data, P for our priority. Where these values will just represent our parameters themselves. And then the first case, the list is empty and the new node has higher priority than the head. So let's figure that out real quick. So if the head is empty or the list is empty, we can say exclamation point head, or if the new node has a higher priority than the head itself, so basically saying this is our head and the new node needs to go in front of the head itself. So wait, no, new node has a higher priority than the head. Oh, basically we want to my mistake. We basically want to create a new node. Let's say n for new node. It's our head, and our head has a bigger value than our new node. So we need to make our new node the new head, and the head will be just part of the list now. So we just also state that our p value is less than our head arrow p. P is the priority itself. And if that's the case, you just need to make sure a new node points to the head, and the head will be the new node. Or in other words, new node arrow next will point to the head itself. So you keep track of that previous head itself, and then the head will now be the new node. Just something from linked list you learned. Sweet lines to represent semi curly braces. So in other words, new node will point to the head, and then our new head, so basically erase this H, will now be new node. Exactly like that. Wow, amazing. So from here, once we check that little condition, we can say that, hey, if the list is on, if the list is not empty, and the new node is not, and the priority of the new node is not less than the head of the head's priority, then we have to traverse and traverse through the whole entire list until we find that perfect little spot to insert that priority, as we did here. Basically, we traversed from head, and we traversed the next variable, which is 5, and we inserted it between 0, the head, and the second value to make room for that value right there. Very rare, we're just going to insert it, nothing else. So create an else statement, or you just put it right there because you already know it. You're basically done. So else, oops, else you're going to basically make a temporary variable. So not pseudocode, not too picky about what is temp, as long as you're pretty obvious what that is. Temp is head, and then you're going to keep traversing until you reach either null, or you make sure you get the priority. So while temp arrow next. So while it's not null, and temp arrow next, arrow p is less than equal to p, which is this value here. So to trace this out real quick, this is our temp, and temp originally had a ghost variable right there. So temp arrow next p is basically 5. And right here we check, hey, is 5 greater than or less than 1? No? Okay. So you keep going. But we would take care of this one in the beginning as well. So you can just say arrow next p is less than equal to 5. So 5 less than equal to 1 or 0 to be taken care of the 0 position itself. Yeah, so basically you want to keep going. So let's say maybe 6 will be a little more easier. Basically, you're going to keep going until that's not true, basically. So let's check one more time just to make sure our code is correct. Because we basically want to say temp arrow next, or in other words, that's a null, and our next p is less than or equal to that p. And if it is, keep traversing. If it's not, you're done. So we can just say is 5 less than or equal to 1, which is no, that's false. So don't go to the next variable. So if it is true, then keep traversing. So you can just say temp equal temp arrow next and sweet. If and then squiggly line to make it a little more clear, squiggly lines. And since that's not true, we can now insert it between these two nodes. So remove the ghost line and write that little portion down here. You can say new node, arrow next will point to temporary arrow next. So as we did earlier, the basically we're doing this little arrow next. We're saying this new node will point to temp arrow next. And then we need to make sure temp arrow next points to new node. We need to do this line now. Temp arrow next points to new node. So we can say temp arrow next is equal to new node. Sweet. And now we're done. That's literally it. But let me ask you this really fun theory question. What's the time complexity? And we can say for case 1, if the list is empty or the new node has a higher priority than the head, we can say O1 because we're just inserting to the head itself and we're swapping head to the new. We can head and the new node will be head. So that's O1. However, if that's not the case, if it's case 2, you have to keep iterating through the linked list. Now we don't have O of 1 anymore. We have O of n. So our time complexity got worse by n times, but we're still pretty good. It's a pretty good time complexity still. Not the best in the world, but for the class, it's pretty good. So this enqueue function increased our original time complexity we had on a regular priority queue. So, which is exactly what we're looking for. Because remember, in our theory, I suggested that our enqueue will have a O of 1, which is true still. This will be O of 1, especially this section right here will still be O of 1. But sadly, this section down here, since we're traversing the whole entire list, will not be O of 1. This would just be O of n. So write this down. O of 1 right here. O of 1. So we're just adding to the head. But this sadly will now be O of n, worst case scenario, because we have to traverse the whole entire list. and then insert it to the back of the list if the priority queue is that high. So sadly, our queue function did increase. Okay, it's pretty fast still. It's a priority queue, and it's a linked list too. So memory wise, we won't be that punished, but we still have a little interesting note to have. So we have the answer key right here, and we can move on real quick. So now let's worry about another enqueue function, except this one will be based on unique values only. And so here we can say that we cannot have a queue that has a duplicate values. So let's say our queue is 0, 1, 2, 5. And I want to insert 5, but it's only be unique values early. So we cannot add 5, but we can add 4, we can add 3, but we cannot add 3 again. Those are not unique anymore. So this little priority queue, well, little queue itself, not priority queue, will have an enqueue function that only adds unique values. So in pseudocode, you can say that we have a func enqueue again. Oof. Enqueue, and then let's say we have value this time, val for short. And you can check if this value already exists. So if val in queue, then we can say, I would prefer to run an error. So just say throw duplicate error. And then once you throw this, you're basically done with this program. But let's say it's not, it's a unique value. And this queue not only is a linked list, but let's practice one more time to append to a linked list, except just a regular linked list, nothing too fancy. So like your insert functions, we can just have this real quick, except this is a circular linked list with circular queue, which is a different implementation than what you're used to, but it's just good practice to know how it looks like. So you can say if the rear itself is not empty, and the rear, if we look back, it's just the end. Back here. You're basically saying if the rear is empty, then we have to redeclare our rear as the front, and the front will equal to the new node itself. Or in other words, say this. Front is equal to our rear and equal to the new node, which I skipped in this case because we already seen how we can declare new node. And if you want to know how to redeclare it, it'll basically just be new node equal to new node val. That's it. And make sure to declare this as a pointer. So remember, this is a pointer structure. It's a linked list. Node pointer. But pretty using this multiple times already, so I won't be too buggy about that. Duplicate that. Sure, we can use a mix of curly braces and dot dots for now. So that's what we're saying. If it's empty, make the front equal to the rear, where the rear will now be the new node. Nothing else. Else, that's not the case. We just add it to the back. We can say rear arrow next will point to the new node. And a new node, once we write this statement, if I can spell node correctly, and then we can just say rear is now the new node. Basically, the tail or the head is the new node. And this is a circular queue implementation. We're not going to be testing on this, but just really good to know. And that's it. Basically, it's a really fun thing to do. But yes, you can write this as a statement like this if it's if it's a theory, if it's a pseudocode question, completely valid. But if it's in code, then I actually did implement this function exist code, and you can find it inside this GitHub link, which will have the unique CPP circular queue. Which, if you don't know, you can create a function called round robin. One of my favorite, but Gobblegum's like using COD zombies, but a little bit more different here, sadly. But yes, very good to know for circular queues. But you don't have to worry about that for now. So hopefully we're feeling okay. It's been a really long time now. Damn, I gotta hurry up. But you know, patience is key. So let's move on to the next topic. Stacks. Stacks is similar to queues except different acronym. We have LIFO instead of FIFO, where LIFO stands for last and first out. In other words, the limit we push to the end comes out first. That's really it. Like stacks, like a stack of books. You keep pushing to the top, and then the top will be popped out first thing. And since we're only working with the top value every single time, it's the same complexity as checking or inserting into a head of a linked list. It's always gonna be O of one because you know what the top is. So if you add it to the beginning and you pop it from the beginning, it's O of one. You don't have to worry about traversing the linked list. You already know what the first value is, and you're basically good to go. So a little theoretical side now. How can we do this with linked list? So we know our node structure needs to include a few things. And theoretical wise, aka in pseudocode from my end, because there's a paragraph for the answer key, we need to have a node structure that will hold the data and the pointer itself. There's like any other linked list. So you can say a next pointer if you want to. Excuse me. Nothing else. And so let's draw this out real quick. So the stack will have like this. The top will be the head, and then we'll point to the next part, point to the next one, and then point to the next one. Well, this will be our head, and each other value will point to the other side. Or if you want to see it like this, it's our head or top, point to the next one, point to the next one, point to the next one. It's not that scary once you actually draw it out. So instead of having a head variable, you can call it top or call it head depending on how you want to view this. So pushing to an element, it's not too bad. Pushing is pretty fast since you only have to push the top of a stack. So let's say I want to add this variable, which you need to add it to the stack. If you want to dequeue, you need to pop it from the head, it's from the top itself. So this is push, this is pop. So theoretically wise, we can write this down. Our push function would just be a fancy word of saying insert to head. Nothing else. Pretty fast. And since we already done inserting to the head multiple times already, you can just say this will be done in O of 1. And the only changing part is making sure we changed up the pointers themselves to point to the top now. And our pop is a little more different. It's like a delete function, except we're only deleting from the top of the head itself. So you just want to pop an element out of it. So you can just update the top pointer to point to the next variable and return that remove node. So delete at head if you want to be more fancy. Delete at head. Still O of 1 because you're only accessing the head. And before you pop it out, you need to make sure you do head. Arrow next is the new pointer. So point to the new head itself. We will actually say this in temporary variable itself because we need to make sure we save that. So we say delete. We can say temp is equal to the current head itself. Head will now be the new, will point to the next variable, temp arrow next. We can delete, or we can just say return temp to make sure we get that value when we pop it. So, and then once you return it, make sure you delete it from the stack. And since you're only accessing the head the whole entire time, you know that it's going to be O of 1. It's pretty fast as well. So whenever you see something like new, like stack on linked list, like what the fuck, just know that you're always, it's just a fancy way of saying it, only use the head, nothing else. So in theoretical, there's a whole entire paragraphs here saying how to do the node structure. The top of the stack will be the head itself, or you could just call it top, depending on how you want to do it. Push, push something to the top of the stack itself. When you push it, you create a new element, the same stuff you done usually, and you set that to point to the top corner, and then redefine that node to top equal to new node. And it's since you're only using the head, it's all one, and because you only have to change a few pointers, nothing else. And pop, exact same thing. Remove from the top of the stack. When you pop it, make sure you make a temporary variable of top or head, and you make sure your top will point to the next pointer, and then you delete or return the top node itself. And since you're only deleting and you're only accessing the head pointer itself, it can be done all of one. It's pretty fast, and it's also really cool to implement if whenever you have the chance to do it. Hint, hint. So one of our so close to our last topic, let's do a brain workout time. So as we covered linked list stacks, and since you did Q linked lists in your labs, what other linked lists can we do? And no, they're very challenging, as you have seen, but they're not that bad when you break it down. So yes, it is possible. And like sorting, because sorting you do multiple things as well. You can implement these structures using linked list, as you saw right now for stacks and what you did for queues in your lab. You can do a queue based on stacks. A little bit annoying. Got that from my exam question, but pretty fun to do whenever you have the free time. And you can also use trees to create stacks and queues. But since we have not covered trees yet, that's for a later topic. So your to-do list for tonight, for a little more studying, is to implement these different variations of stacks and queues. And you should really focus on the priority queues as well. Don't forget those. Don't forget those. Those are really important. So after this very long exam review, hash sorting took like the longest. You got to hash it. And so hashing is pretty new. If you have taken Python before, and I hope you have because it's a wonderful language, hashing is a really, really weird way of saying it's a dictionary, nothing else. And so if you think of it in a dictionary way, it's actually a lot easier. So hashing is just mapping elements based on a key onto a hash table, nothing else. We can make a key based on our hx function. So this little function right here. This will determine our hash function will determine our key, how to make that key itself. Most common one will be either based on the size, or you'll be just given a value itself or giving it to you directly. Do not have to worry about that too much. And then there's some basic functions like pushing into a hash table and finding a value based on the key in a hash table. Time complexity wise, with collisions, you have all of one best and average time. But if you do collide, you need to find the next available spot. And that does take a while because if you need to find next available spot, you have to search through the hash table. And since you have to search through the whole entire input size, it's O of n. Same thing with the find. If you don't find it there, you have to find it through the whole entire next available spot it can be at, which is O of n because you don't know where it's at all. But if you have no collisions, it's O of 1 because you know it's gonna be there no matter what. It's like boom, instantaneously it'll come up. It's amazing. So you can visualize it. There's the code right there as well for all types of hashing. I think included linear, direct, and chaining. the ones we're going to cover in this mock question. Oh, spoilers, by the way. Mock question, the number 6, the last one. Thank God. It's gonna be, excuse me, hashing this array down here, this lovely array we have volunteered, and using direct, linear, and chaining. And since we have to do a lot, let me add a page because I did not add enough space here to do all three. Add a page, sure. So let's do problem. So let's do linear. So let's make sure we have this array. So our array is gonna be 54, 75, 24, 45, 18, and 10. And then our hash function will be divisible by 10. Good to know. Hash table, size of 10. So we can create a array saying that we have, oh shit, might be a little bit too big. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have size of 10. So with that in mind, we can start. So the first one is direct. So direct does have collisions, and if it does collide, we can not find the next available spot. We just have to say, fuck you, stay there. You cannot join our table at all. It's like high school all over again. It's crazy. So let's do direct hashing for this function right here. So let's copy this real quick. So we don't have to do this, like we don't have to do like same table multiple times. And our hash function is pretty easy. You just divide it, you find the mod divisible by 10. So this is the first value. So 54 mod 10 has an index of 4, or key of 4 if you want to be more specific. So we'll do down here, and our keys will be signified by k, where k will be 4. So we can add that to the table. 54, 4. Sweet. Next number, 75. So that has an index of 5, which is 75 mod 10 equal to 5. So we put that into hash table 75. However, 24 has the exact same key as 4. And now we have collided. But this is direct. So we just ignore it. We do not add it to the table. We say, screw you. You cannot join our cool group table. Same with 45. 45 has an index of 5. So ignore, bully him. I don't know, do whatever you want to. Just ignore him, basically. But now, let's check the next value, which is 18. And 18, or index 8, is not filled out at all. So we can add that right there. We'll be good to go. So now let's check 10. And 10 has a value of 0. And we can add 10 to our table. And that's it. We're done. Direct is pretty fast. You don't have to worry about the next available index, unlike chaining and linear probing. So nothing too difficult. But yeah, if you ever collide, just ignore that value. It basically is like giving us an entry bit to that number itself. And any other future numbers that give that exact position. When we collide, we ignore. It's just like a traffic accident. And we can look down here. In our answer key, we have reached the exact same conclusion. We have 0 at 10, 54 at 4, 5 at 75, 8 at 18. Oh shit, I forgot about 10. And 10 at 0, which there is a duplicate 10 here, which should not be there. So I'll take that out in the official release. My mistake. So good to go, good to go. Probably did the exact same mistake in the other ones, but oh well, that's okay. So let's duplicate this page so we can keep using this for the next one. Oh, hello. Crazy. What did I do? I did something. You know what? That's more than I can say like every single day. So, I guess. Please be there. I paid whatever. So, yeah, now let's do linear. So, exact same thing again, except let's do it with when we collide, we make sure we we can find the next index itself, which is linear probing. So instead of doing direct, let's do linear. So linear, as I'll say one more time, basically involves when you collide, you don't have to ignore that value. You can actually find the next available spot in the hash table and add that variable directly. So again, 54 mod 10 is 4. So we add 54 to position 4. 75 has index 5 again. 75 mod 10 is 5. 75. But we do collide here. 24. We get 4 again. However, we can take care of that by finding the next available spot from 4 to above. So let's check. 4 is occupied. 5 is occupied, but 6 is good to go. So we can add 24 to index 6. And now we check again. 45 has an index 5, but 5 is occupied. So check the next one. 6 is occupied, but 7 is free. So we add 45 to 7. So now we check again. 18 has a position of 8, but that's not filled in. So we can add 18 right here. Then we have 10, which is 0, and we add it back to the first position, which is exactly what we're looking for. But however, let's say we do run out of space. What happens then? That means it's inefficient. It's not one of the best hashings, but it'll get you far enough before you realize you're out of space. So that's okay. So now, hopefully, I think the answer is correct. Yeah, it's correct. I just added duplicate 10 for some reason. Basically, it's the exact same idea we have here. So let's do it one more time, but for hashing. And so for hashing, if I can get this iPad to be nice, that's linear probing. Oh, fine. So for chaining, chaining requires us to do something a little bit more different. We will basically build upon linear when we collide, we won't just ignore the value, but we will chain on the next value. And once you did your lab, I recommended using a dynamic array. A little bit more easier to implement, but you can also do it linked list wise. But so it's completely up to you how you want to do this. So when we trace it, we can just do it as is. So 54 again has index 4. We add that to position right there. 75 has mod 5, so we add 75 right here. 24, however, does collide with index 4, so we will chain on to the next variable. So in a 2D array, we just add a block here and add 24. Or in a linked list, you just make a new node, point to the next node right there. 45 again, does collide, so we add index 5. We add a new little insert right here. We add 45. And then from here, we move on to the next value. So as you can tell, we're not finding the next position. We're just chaining along at the exact same index every single value we get from here on out. And then 18, position 8. So we have 18 right here. And 10, position 0, as we've done so multiple times already. That's it. So we have a very weird chaining where the rest of these values will be empty. And this is how training's going to work. And hopefully I got it right with that mysterious 10 still there. And this is exactly how our answer key should look like, with collisions at index 4, index 5 for chaining. But for linear probing, I included index 6, index 7 to show this our next available spot. And yeah, that's about it. Hashing will be one of the easiest topics ever. And I'd recommend doing this one first. So you can spend a lot more time with the other questions. Hint, hint. So yeah, if you have any questions, and I'm really sorry that I had so many mistakes in this review, but anywho, hopefully I'll fix them before the official release. And whenever I do go over that, I'll make sure to have everything ready to go. So any last tips I can give you, study well, have a good night's sleep, don't stress too much. I hope you don't. And remember, you always got this. Take your time, and you have 2 days to take the exam. First part is going to be programming. So you could probably ask us some ideas on how you want to do it, but we can't really debug it for you. And the second day will be theory, which is mostly this part. So good luck. You got this. Look at the code for the programming section, theory, go over the slide it however much you need to. And yeah, good luck, guys. You guys got this. And yeah, good night.